general theorems and practical procedure, how do you renormalize in general at the multi-loop level? What we say is specific for dimensional regularization, which is of course in practice the most important scheme. And we use perturbation theory, of course. So what is necessary is that you renormalize your theory at, in principle, all loop orders. And in principle, you might want to calculate quantities, physical observables, also at all loop orders. And you must do that iteratively by starting at tree level. Then you do one loop calculations, one loop renormalization. You need to use the one loop results to do two loop calculations and two loop renormalization and so on. So it is an iterative process. And let us begin by starting this iteration. So let us say we are now at loop level number n, which is 0 or bigger than 0. So maybe we have already done some work. And we assume, so let the theory be correctly renormalized at this loop level. Up to order n. When I say order n in this chapter, it means n loop level. What do I mean when I say correctly renormalized? It means two things. First of all, if n equals 0, it means we are at tree level or at the classical level, because loop diagrams are proportional to h bar. So we are at a tree level. Then the theory is defined by the classical Lagrangian, which is the Lagrangian that you simply write down by L. And to make it clear, I often have a subscript CL for classical. But in this context, I will also call it L with a superscript 0 in brackets, which is obviously the 0th order of our iteration. And this Lagrangian is a local Lagrangian, local expression in terms of our fields and its derivatives. It is relativistic and also Hermitian. And it determines the Feynman rules. So if n is bigger than 0, then we have already done some work up to the n loop level. That in this case we assume we have already constructed the renormalization up to this order. And what that means is that we do not only have the classical Lagrangian, but we have something that we call bare Lagrangian. A bare Lagrangian defined up to the order n, which I denote as bracket n superscript. And this is a combination of the classical Lagrangian, L0, plus a so-called counterterm Lagrangian, CT stands for counterterm, with index 1 for one loop, plus and so on, with counterterm with superscript n. And the superscript without bracket means strictly n loop counterterm Lagrangian, and the superscript n in brackets means up to n loop. So we have constructed in our iteration so-called counterterms, which are additional terms in the Lagrangian, which have coefficients of one loop, two loop, and so on order, and which in total provide a modified Lagrangian, which however is still local, relativistic, and Hermitian. And all of these Lagrangians are defined, since we work in dimensional regularization, in d unequal to 4 dimensions, which means that we work in dimensional regularization. So in all these cases, regardless whether we work at tree level or at higher orders, we have a Lagrangian at our disposal, and the Lagrangian generates Feynman rules in the usual way. So we have a set of Feynman rules which in general include so-called counter-term Feynman rules. And the theory is defined by these d-dimensional Feynman rules. Okay, so this is the first item in our assumption that we need at the n-loop level. And the second item is the property of the theory at the n-loop level. So we have constructed these counter terms and the so-called bare Lagrangian. And what is its property? It makes the theory finite, of course. So this is the statement that up to the order n, the theory is finite. That means, let's say, for example, at the order n equal to 2-loop level, we would have, for example, the following situation, that we can perform the limit epsilon going to 0 of the following. For example, we take a 2-loop Feynman diagram in QED. It might look like this. This is the photon self-energy at the 2-loop level. 2 external photons, an electron loop, and another photon, which is a nice 2-loop diagram. We add to it, of course, all other 2-loop diagrams, but we also add diagrams which are of 2-loop order and which involve a counter term coming from our 1-loop counter term Lagrangian. Such a counter term could look like the following Feynman rule. Namely, in the counter term Lagrangian, there might be a term which gives rise to this Feynman rule, again photon, electron, electron, but with a coefficient which is of 1-loop order. Therefore, this diagram is of 2-loop order. And here we have a vertex from the 1-loop counter term Lagrangian. Plus, of course, all other 1-loop diagrams with 1-loop counter term insertions. And ultimately, we also add a diagram like this, where this here is a vertex from the 2-loop counter term Lagrangian. So this is a 2-loop counter term. In this case, it would be a term which has just 2 photon fields attached to it, some operator with 2 photon fields, and a coefficient which is of 2-loop order. And then all of these diagrams are of 2-loop order. They are all added up, and if you add them up, then the limit epsilon going to 0 exists. And this then defines the physical result for the photon self-energy at the 2-loop level. So this is the statement that the theory is finite, and so this should work, of course, for all Feynman diagrams and all green functions. So this is the start of our iteration. So we have already worked up to this point such that at some arbitrary n-loop level, the theory has become finite by adding certain counter terms. And now let us discuss what we need to do in order to go to the next order. And then also how to use this approach and the construction to calculate physical quantities. So the procedure at order n plus 1, let's say begin. So you now want to work at the next order, for example, at the 3-loop level. So what you need to do is, first of all, to compute Feynman diagrams. And it's sufficient to work with one particle irreducible Feynman diagrams of order n+1 loop level. And you have the Feynman rules at your disposal with counter terms up to order n. So you compute these diagrams with the Feynman rules from the bare Lagrangian up to the order n. And as an example, let's say n+1 is 3, so that continues this example here. This is now established. Now, what can we do with it at the 3-loop level? At the 3-loop level, for example, we can calculate an electron self-energy in QED, electron self-energy with a photon loop. And so it could be this Feynman diagram where you have an electron self-energy with a photon loop, but the photon itself undergoes a 2-loop correction. It undergoes the 2-loop correction from here. So then this would be a 3-loop diagram, and you need to calculate the electron self-energy at the 3-loop level using the Feynman rules from before. That means you must automatically add to this also such diagrams. So in this case, you would add here this diagram with a 1-loop counter term insertion plus this diagram with a 2-loop counter term insertion. Then all of these diagrams are of 3-loop order. And of course, you must be complete. You need to add all diagrams of this kind. And then you obtain a result, which is probably not finite because we have not yet renormalized our theory at the 3-loop level. But we need to compute the result of such Feynman diagrams first and then continue. Yes?
In the diagram in the middle, do I need to add up another diagram where the other vertex?
Yes, yes, yes. And there are many more diagrams. For example, there would be also such diagrams where a counter term is here, where the counter term is there, where the counter term is here, where the counter term is here and here, everywhere. There are many such diagrams and you need to add all of them. You must be complete. You must calculate all diagrams of this order using all Feynman rules from the previous iteration step. And there will be all such diagrams. If you make a mistake, you will see it, and how you will see it, we will soon discuss. You will inevitably obtain results which can't be correct, and we will discuss how you can see this. Okay, so you do this, you obtain some result, you write it down into a Mathematica file or whatever, and now there are two theorems which I want to explain to you, which apply and which are relevant to discuss the results that you might or might not obtain here. So the first theorem, let's call it theorem 1, is a theorem which comes from, let's say, a theoretical approach, which is often called causal perturbation theory. And this is associated with Bogolyubov and collaborators. It's basically already written in the ordinary Bogolyubov quantum field theory textbook, and it has been made more mathematical by Epstein-Glaser. And this approach tells us the following. I already alluded to it in the exercise, namely in any approach to regularization and renormalization and loop calculations, the imaginary parts of these Feynman diagrams and of green functions are not arbitrary, but they are fixed by a very physical requirement. Namely, by which requirement are they fixed? How we remember? Yeah. By the optical theorem, in other words, more generally speaking, by unitarity of the S matrix or unitarity of time evolution. So the imaginary parts are fixed by the optical theorem or by unitarity. And therefore, whenever you have a correct procedure, the imaginary parts must always come out in agreement with the requirements of the optical theorem. Therefore, in principle, by the way, you do not have to do the 3-loop calculation explicitly by evaluating loop integrals. You could just go to the optical theorem and actually really use it to determine the imaginary part directly. And then you circumvent the calculation of those diagrams, and you also will not encounter divergences, but you only get the imaginary part. That's what he did in his bachelor thesis. So this gives you the imaginary part, and they are unambiguous. How about the real parts? The real parts are also to a large extent fixed by physics. The real parts are fixed, and that gives the name to the approach, namely they are fixed by causality. Causality, you can prove, gives rise to analyticity of the green functions, which are determined by Feynman diagrams, in a very specific way. So if you regard all the Feynman diagrams and green functions as functions of momenta and masses, and all of the arguments are taken as complex variables in the complex plane, then the functions must have certain analyticity properties, following from causality, which is implemented, for example, in the so-called Helen-Lehmann representation. Which is one way how to see this connection. So the real parts are then fixed by analyticity, and analyticity mathematically simply means that, of course, the imaginary part and the real part are not independent of each other. If you know the imaginary part, you know a lot about the real part. However, you do not know the real part completely, because there are functions which are completely real, and they would not change the relationship between imaginary and real parts, for example, polynomials. And that means that the real parts are fixed up to polynomials. Up to polynomials in external momenta. And often we think in terms of Lagrangians. If we are in momentum space, a polynomial in momenta becomes a local expression in the Lagrangian with a finite number of derivatives, because momenta become derivatives. So, and then a polynomial is a local term in the Lagrangian. So we can say the real parts are fixed up to local terms. We can add local real terms. So the only thing which is not fixed by these deep physical principles, unitarity and causality, are local terms, which are exactly the terms which can be written in a Lagrangian. Everything else is fixed by unitarity and causality. Imaginary parts and non-local terms are fixed. that is the first theorem, which is general and not only valid in dimensional regularization, but in any approach to renormalization, because it just comes from analysis of physics. Then the second theorem, which applies to dimensional regularization, and it comes from Speer and also from Brighton, Lohner, Mason. Is the following statement on dimensional regularization. So it is the following theorem. Let me write it here. In dimensional regularization, first of all, the imaginary parts and the non-polynomial real parts are correct. That is the first very important and non-trivial statement. So, and this is the theorem which I mean when I say that dimensional regularization is one of the possible consistent regularization schemes, because it is consistent with unitarity and causality in the sense that it provides the correct output which is required by those physical conditions. And if you would invent your own regularization method, then you would have to check the same statement. For example, there was this clever student who was not really satisfied with divergences in quantum field theory, and he said that, okay, since we anyway are dealing with unreasonable mathematics, why do we not just set all the integrals which are divergent to zero? Okay, if you set everything to zero which is divergent, what is so bad about this choice? And here is the answer. By setting integrals to zero which are divergent, you kill the necessary imaginary and non-local real parts, so such a procedure would not be compatible with unitarity and causality of quantum field theory. Therefore, you must do something more advanced than simply dropping everything which is divergent. Okay, so dimensional regularization is correct in this sense. Then and this is basically what Speer said immediately in his paper. Now detail about the ultraviolet divergences. And the statement about the ultraviolet divergences in short is that at the multi-loop level, if you do it like I described, for the final result, it is exactly as at one loop order. So the divergences are again polynomials in the masses and momenta, and they are 1 over epsilon poles as at one loop order. But this result is only true after you add all these Feynman diagrams with counter terms of lower orders. So these Feynman diagrams are important to cancel these subdivergences which appear in the three-loop diagram. And after you have cancelled all the subdivergences, what remains is a structure which is similar to one loop. So let's write this down. The ultraviolet divergences are polynomials. First of all, in 1 over epsilon. And we also know the degree of the polynomial, namely the degree is the loop number, up to 1 over epsilon to the power n minus 1. So we are currently working at the n plus 1 loop level. And for every loop, we get 1 over epsilon pole. So we have a polynomial in 1 over epsilon up to this term. And at one loop, of course, only 1 over epsilon. Now, what are the coefficients of all the 1 over epsilon terms? This is a polynomial in the masses and momenta, so the coefficients of these 1 over epsilon to the I are polynomials in the external momenta. And the masses, but I will say a footnote on the masses here later on, and but definitely in the external momenta. And we also know the degree of the polynomial, namely it is like at one loop. The degree of the polynomial is simply the overall degree of divergence of the entire green function. By simply counting all factors in the numerator and all factors in the denominator, collecting all loop momenta simultaneously. So this is then often called a superficial degree of divergence in order to distinguish it to degree of divergence of subdiagrams or whatever. So this is the main statement. You know how many 1 over epsilon poles appear, and you also know that there are no.
طبعا هنا كما ذكرت في الفيديو السابق أن يعني عندما تعمل تحل لاجرانج للتو لوب والثري لوب فإنك يعني في حسب اليو في دايفرجنس فإنك تعمل نفس الون لوب، لكن يعني تضيف إليها بعض يعني تضيف لما تيجي تجمع الكاونتر تيرمز للون لوب والتو لوب وبعدين الثري لوب، يعطي الإجابة ستكون هي نفس الون لوب لكن ستكون بدرجات أقل. طبعا الكاونتر تيرمز هي بولينوميال in external momentum، يعني في النهاية بتعمل اللوبس بتاعتك دالة في الجسيمات أو كميات التحرك الجسيمات المتفاعلة، وبالتالي تستطيع أن تعمل في اليو في دايفرجنس تعمل الحلول بتاعتك على نفس الون لوب، لكن طبعا ستكون مضروبة في كميات أقل. وهذا ما ذهبت له في الفيديو السابق، أنك في اليو في كأنك أنت كبرت الأبعاد، تنظر للجسيمات هذه صغيرة عند أبعاد كبيرة. هذه في بعدين سنأتي الاي ار، ستكون العكس مباشرة. الاي ار دايفرجنت أنك أنت بنفسك ذهبت للأبعاد الصغيرة وتنظر إلى هذه الجسيمات ستكون كبيرة، والتفاعلات ستكون ضخمة، وأن التفاعلات ستكون يعني كما سنرى يعني بعدين إنها تكون تفاعلات كلاسيكية وتطبق عليها الفيزياء الكلاسيكية. لماذا؟ لأن أنت أبعادك صغرت، أنت لما تصغر أبعادك سترى التفاعلات، هذه التفاعلات هي تفاعلات كلاسيكية عادية كما سنرى بعدين. هذا طبعا تعتبر تنبؤ. أما في حالة اليو في فإنك تحتاج لمزيد من الاشتقاقات، مزيد من المساواة باللوكاليتي واليونيتاريتي، وبعد ذلك يعني ستأتيك الإجابة الدالة في المومنتوم لكن بدرجات أقل. يعني مثلا نحن نعرف أن إبسلون أن الألفا هي 1/137. عندما تعمل يو في دايفرجنس ستأتيك في التو لوب والثري لوب ربما يكون 1/37 تربيع وهي أقل، ربما يكون 1/137 تكعيب، وهكذا أقل. ولكن في النهاية أنت تستطيع أن تتخلص من الإبسلون التي ذكرناه في الفيديو السابق أنها تعطينا حسب نظريتي تعطينا تخبرنا عن تلاشي القوة. وهذا واضح أنك أنت إذا اعتبرت ألفا يساوي 1/137 في حالة تو لوب تكون 1/137 تربيع، في حالة مثلا ثري لوب يعني مثلا 1/137 تكعيب. نجد هنا أن الدالة في الاكسترنال أو في كمية التحرك الخارجية تقل شيئا في شيئا، وهذا التقليل أي أن الفضاء الداخلي لا يتأثر بالفضاء الخارجي. أو مثلا نحن نتحدث عن high order of loops كدالة، هي عبارة عن بولينوميال دالة في ال external masses و momentum. يعني مثلا عندنا إلكترونين متفاعلين، فاللوبس تكون دالة في كمية تحرك الإلكترونات وكتلها، وهذا شيء جميل جدا. نشتغل الون لوب ثم يشتغل التو لوب، وعندما نأتي للثري لوب فنجد أن الكوفيشنت مثلا ألفا اللي هي 1/137 في الون لوب يساوي 1/137 في التو لوب يساوي 1/137 تربيع. إذا نقصت الثري لوب 1/137 تكعيب مثلا. وهذا يعني أن اللوبس الداخلية كدالة في الكتل والمومنتوم للإلكترونات التي هي عبارة عن لوب خارجية تقل، وبالتالي تنفصل اللوب الداخلية عن اللوب الخارجية. هذا يوضح نظرية علي يوسف، وهذا صحيح جدا مع نظرية علي يوسف. لأنه نظرية علي يوسف عندما تتحدث عن اللوبس الداخلية فإنك تتحدث عن ماذا؟ ما يسمى بالتايم كونتراكشن والسبيس كونتراكشن. وهذه هي الكونتراكشنز تزيد كل ما تحدث عن صغر بعد، كل ما تزيد هذه الكونتراكشنز، ما في النهاية يؤدي إلى ماذا؟ يؤدي على فصل الفضاء الداخلي للتفاعلات هذه اللوبس الداخلية عن الفضاء الخارجي. بالتالي أنك ستأتي وقت لا ترى فيه شيئا ولا تعرف فيه شيئا، لكن بموجب نظرية علي يوسف يمكن أن تتنبأ بما يحدث في هذه اللوبس الصغيرة جدا جدا أو اللوبس المتقدمة جدا جدا. هذا بالنسبة لليو في دايفيرجنت. عندما سنأتي إلى الاي ار دايفيرجنت هناك تغيرات كبيرة جدا ستحصل. ستكون أولا دايفيرجنت لن يكون في واحد على إبسلون، تكون في شيء آخر، وبعدين الشيء الثاني سنطبق الفيزياء الكلاسيكية بطريقة ريحية. لكن أيضا هنا أنت نقلت الملاحظ من ملاحظ خارجي في اليو في دايفيرجنت تعتبر ملاحظ خارجي، وترى اللوبس الداخلية، وبالتالي أنت تفقدها شيئا في شيء. لكن في حالة الاي ار دايفيرجنت أنك ستكون ملاحظ داخلي، وبالتالي يجب أن تكون الأبعاد بالنسبة لك أبعاد عادية، لكن في النهاية أنت ستفقد شيئا سنراه لما نأتي إلى الاي ار دايفيرجنت، لأنه أنت أجبرت نفسك أن تكون ملاحظ داخلي. وإذا أجبرت نفسك أن تكون ملاحظ داخلي فإنك ستفقد التجربة، لأن أنت في النهاية ليس ملاحظ داخلي، أنت ملاحظ خارجي. تنظر إلى التجربة في يو في فعلا أنت ملاحظ خارجي، وهذه الوضع الطبيعي. لكن في الاي ار أنت ستجبر نفسك ملاحظ داخلي، لكن أنت في النهاية ملاحظ خارجي. فهذه هنا ستفقد شيئا آخر بسبب الكونتراكشن اوف سبيس تايم. طيب تعالوا نواصل.
Other singularities like logarithm of epsilon, stuff like this, doesn't exist in dimensional regularization, and the coefficients are polynomials in the external momenta. So now the statement on the masses. It can happen that you decide that in these counter term Feynman rules you incorporate as a coefficient of such a counter term logarithm of a mass. Just decide for it. And if you do that, then of course this statement is ruined by your choice of the counter terms. This is a possible choice. But it cannot be a possible choice to choose counter terms which are logarithms of the momenta, because you cannot write down a logarithm of a momentum as a local term in a Lagrangian. But you can have a term in the Lagrangian phi square times ln m. That of course in principle exists. So unless L counter term contains other functions of M. So about this box.
طبعا هنا لماذا يعني يتم استبعاد البي المومنتوم والام يعني يعني التعامل مع ام كتلة، هذا واضح لأن البي تتأثر بالتايم سبيس تايم كونتراكشنز. أما الام يمكن أن تقول لها هي طبعا في الحقيقة تتأثر، لكن يمكن أن تقول لها تتأثر لسبب ما أنها ستطرد من التفاعل. الام تطرد من التفاعل، لكن البي تتأثر بدرجة كبيرة جدا جدا. وبالتالي نحن عندما نتحدث عن الكواركات داخل البروتون من ناحية اليو في دايفيرجنت، فإننا لا نتحدث عن الكمية تحركاتها، لأنه لا نعرف كمية تحركاتها، لكن نعرف كتلها. فنحن نعلم أن الأب كوارك يكون من يعني 1.5 ميجا إلكترون فولت إلى 3.5 ميجا إلكترون فولت، والداون كوارك من 3.5 لحد 5.5 على ما أظن، و4.7، وهي تعتبر ميجا إلكترون فولت. هذه كتل، لكن ما هي المومنتوم لا نعرف. لماذا؟ لأن حسب نظريتي تقول أن المومنتوم هو الكاينتيك انرجي، الطاقة الحركية لهذه الكواركات تغطي البروتون كله، مش يعني من شدة أنها يعني بسبب أنها عالية أنها تغطي البروتون كله. يعني 3 كواركات كافية جدا لتغطية البروتون كله، ولكن كتلها لا، إذا جمعت هذه الكتل لا تساوي البروتون. كتلة البروتون 1 جيجا، وأنت إذا جمعت هذه ال3 كواركات لا تفوت 10 ميجا، لكن طاقتها الحركية تغطي البروتون كله. ف3 كواركات كافية جدا لتغطية البروتون كله. وهذا ناتج من ماذا؟ هذا ناتج أن كمية التحرك وطاقة الحركة تتأثر مباشرة بالتايم كونتراكشن، يعني بتتأثر مباشرة بوضع الملاحظ. أما الكتلة لأنه بتسبب التايم دايليشن، فهي يمكن أن نعتبرها فيكسد ثابتة، لأن هي تقاوم التايم دايليشن. بلهجة أخرى أن الفضاء ثنائي الأبعاد يحارب الكتلة، لا يحارب المومنتوم، لأن المومنتوم الفضاء ثنائي الأبعاد يؤثر عليه بقوة، فلا يحارب المومنتوم ولكن يحارب الكتلة. وبالتالي بما أنه يحارب الكتلة، فبالتالي يمكن أن نعرف سلوك الفضاء ثنائي الأبعاد بدراسة سلوك الكتلة. لكن إذا طورنا أجهزتنا، إذا تم تطوير الأجهزة، يمكن ندرس سلوك الفضاء ثنائي الأبعاد بدراسة المومنتوم وكمية التحرك والطاقة الحركية. لكن نحتاج هنا إلى أجهزة حديثة جدا تقيس لنا في مدى لأزمان صغيرة جدا. يعني كما سمعنا أن الآن هناك علماء يدرسون حركة الإلكترونات من زمن قدره الأتو سكند. يعني بروفيسور أحمد زويل توصل إلى فيمتو سكند، وهي التفاعلات الكيميائية في الطور الغازي نأتي للأتو سكند ودراسة الإلكترونات حول الذرة. طيب لماذا الأتو سكند يخبر عن الإلكترونات حول الذرة؟ لأنها تستطيع أن تقيس المومنتوم العالي جدا والتي تؤثر فيه الفضاء ثنائي الأبعاد والأبعاد أبعاد هذه أبعاد الذرة وأبعاد المدارات الداخلية للذرة. لكن من ناحية الكتلة لا نحتاج لهذا، لا نحتاج لأتو سكند، وإنما نحن فقط نحتاج إلى أن نعبر عن الإلكترون بأنه سحابة إلكترونية، وندرس الفيزياء لهذه السحابة الإلكترونية. لا نحتاج إلى مومنتوم للإلكترون، ممكن التنبؤ بها لكن لا نحتاج إليها. ونعتبر الفضاء الإلكترون عبارة عن سحابة إلكترونية وندرسها ونجعلها دالة بالنسبة للنواة، دالة بالنسبة للنواة، لأن النواة كتلتها صغيرة، فسحابة إلكترونية كدالة في النواة، الموضوع يمشي تمام. وبالتالي المومنتوم نعتبره مومنتوم للنواة ونعمل الإلكترون هي دالة بالنسبة للنواة. هذا بالنسبة ليو في دايفرجنت. نعم.
Here is a very important and extremely powerful statement on multi-loop calculations in dimensional regularization, and it basically explains the procedure of renormalization at all orders. Yes?
One loop level, we had the fact that the coefficient of the 1 over epsilon and the coefficient of the physical mass or the physical quantum was the same, and we argued that that would be in one loop always.
The coefficient of mu square, you mean, ln mu square was the same.
Yes.
So the unphysical mass.
Yes.
Yes, so it's not the physical mass, but the unphysical mass scale mu, ln mu square and 1 over epsilon has the same coefficient.
Yes.
This is the statement that you have in mind. And there are similar statements at the multi-loop level, however, that becomes more complicated because the ln mu square appears in different ways in all these different diagrams. So for example, in the left diagram, you really have, instead of mu, so you have mu to the 2 epsilon at first. So in the left diagram, you have mu to the 6 epsilon because it's 3 loop. But in the next, you have mu to the 4 epsilon because it's 2 loop. And here you have mu to the 2 epsilon because it's actually 1 loop. It's of 3 loop order because of the counter term coefficients, but it's 1 overall loop, which gives 1 factor of mu to the 2 epsilon. And so therefore, this relationship between 1 over epsilon and ln mu square becomes more convoluted. You can still trace it back in a similar way, but there is not this simple relationship anymore. Okay, so this is a very important result. So, and that forms, of course, the backbone of our procedure of how to go on in our loop evaluation and in the renormalization procedure. So we started our procedure at the n+1 loop level, compute all the one-particle irreducible diagrams using the counter-term Feynman rules from lower orders, which have made finite the theory at lower orders. Then this theorem applies to exactly this case. That means the divergences from such a combination is now a polynomial in 1 over epsilon and a polynomial in the external momenta and the masses. Therefore, we know that we can cancel the divergences by adding to the theory yet another counter-term Lagrangian, which cancels these local terms. So, therefore, to say it simply, the form of the UV divergences is the same as the form of Feynman rules derived from yet another local Lagrangian, which is of course also relativistic and Hermitian. So in the non-Hermitian part, there cannot be divergences because the non-Hermitian part is the imaginary part which is fixed by unitarity, and that is finite, and we have already said that dimensional regularization is in agreement with unitarity. Therefore, it produces the correct imaginary parts, which therefore are also finite, so the divergences can only correspond to real parts and therefore to Hermitian Lagrangians. And it is local because the result is, which is of course also relativistic and Hermitian. So in the non-Hermitian part, there cannot be divergences because the non-Hermitian part is the imaginary part which is fixed by unitarity, and that is finite, and we have already said that dimensional regularization is in agreement with unitarity. Therefore, it produces the correct imaginary parts, which therefore are also finite, so the divergences can only correspond to real parts and therefore to Hermitian Lagrangians. And it is local because the result is a local divergence. And please note that this locality of the divergences corresponds to the fact that the non-local terms had been defined unambiguously by causality and analyticity. They are unambiguous and also finite automatically, so the divergences are only in those terms which are not fixed by anything, the local real terms. And they can be cancelled by adding a local Hermitian relativistic Lagrangian to the theory. So the required operators in this counter term Lagrangian depend on the divergent one particle irreducible diagrams. So only diagrams with degree of divergence bigger or equal to 0 matter. So therefore, in order to know which terms in the Lagrangian in principle could arise at all, you can first of all generate a list of all green functions that are possible, calculate the overall degree of divergence for all green functions, and select the ones for which the degree of divergence is positive. This is maybe a finite number, and then you know which operators can possibly appear in your counter term Lagrangian. All right. So with this in mind, we can now go on with our procedure at the n+1 loop level. So let us continue with our procedure. First, we now define indeed our counter term Lagrangian, L counter term n+1 loop order, which we now know to exist, which cancels all the divergences. Such that the theory is finite at the n+1 loop level. This is the main thing, and we now know that such a counter term Lagrangian can be found. After you have made the theory finite, or in parallel to it, there is something else you typically want to achieve, namely the counter terms can also have finite.
طبعا كلمة finite counter term والfinite هو يؤكد ما ذهبت إليه قبل قليل. لماذا؟ لأنه نحن نعتبر الكاونتر تيرم كاونتر تيرمز هي دالة في الاكسترنال مومنتوم وماسس. طيب ما يحصل هو كالآتي، أنه بقية التيرمز ستكون دالة تناقصية في الماسس والمومنتوم، وبالتالي إلى أن نصل إلى الزيرو. يعني الترم الأخيرة هي عبارة عن زيرو. يعني مثلا أفرض أن الترم الأخيرة عبارة عن يعني ماس مثلا ألفا في، أو مثلا نقول A في M1 زائد B في M2 باعتبار أنه إلكترونين، وأمامهم coefficient عبارة عن 1 على ألفا اللي هو 1 على 137 أس 7. كم تكون هذا؟ 1 على 137 أس 7 أو أس 10 أو حتى أس 20. وبالتالي يمكن إهمال هذا الحد، بالرغم من أن المومنتوم داخله يكون عالي جدا. المومنتوم داخل هذا الحد لأنه الأبعاد صغيرة تؤثر بقوة على المومنتوم. فإذا أهملت هذا الحد، إذا تعاملت مع الماس، فإن المومنتوم سيكون يمكن إهمال المومنتوم عادي، وبالتالي يمكن تهمل هذا الحد بالكلية، ويعتبر إنه هذا الحد عبارة عن عبارة عن يعني فاينايت. بالتالي هذه المعادلة كلها تكون عبارة عن فاينايت، لأن هي دالة في الاكسترنال مومنتوم والاكسترنال ماس. حتى الكوفيشنت هي دالة في هذه الكميات الملاحظة.
Parts, the counter-term Lagrangian doesn't only have to contain 1 over epsilon poles, you are simultaneously allowed to add finite counter-terms. Because remember, analyticity plus unitarity fixes everything except for local Hermitian parts. So nothing can stop you from adding here not only 1 over epsilon poles, making the theory finite, but also simultaneously adding arbitrary finite parts which are still local and Hermitian and relativistic. And actually, you cannot really separate very unambiguously between divergent and finite contributions, because what is divergent and what is finite depends on the regularization method that you choose. So typically, simultaneously with this, you also add finite counterterms if required, and normally this is required. Adjust, and adjust is always required, so you fix what the finite parts are, and even setting them to 0 would also be one way to fix the finite parts. So adjust the finite parts of L counter term n plus 1 to achieve two purposes. Namely, the first purpose is to restore symmetries which may be broken by the regularization. And this sometimes happens, and it will not happen probably in this lecture. So in our lecture we will not need this here.
لماذا الريجولاريزيشن تكسر السيمتريز؟ طبعا هذه معلومات خفايا يمكن أن تفسيرها نظريتي، وهناك أشياء كثيرة فاتت علي في هذه الملاحظة، لأنه في هذه المحاضرة أنا في الحقيقة يعني هناك أمور ما تشغلني، لهذا هناك أمور كثيرة كما يقال أن الشيطان يطبع في التفاصيل، هناك تفاصيل كثيرة فاتت علي. لكن تعال نعرف لماذا الريجولاريزيشن يكسر السيمتري. هذا طبعا يعني بس يعني ربما يكون قد ذكرته على مضض، ويعني والآن سأحاول أن أسترجع معادلات الريجولاريزيشن سواء معادلات، لكن أنا ما أعلمه حاليا أن الريجولاريزيشن هو أن الكتلة الانفيزيكال ماس اللي هو ميو لين ميو ستكون أسي ألفا أسي إبسلون، وإبسلون هذه صغيرة جدا، وبالتالي نجد أن الكتلة الانفيزيكال ماس يعني الكتلة غير فيزيائية تصغر بواسطة الميو، ونقصان الكتلة يكسر السيمتري كما لاحظنا يعني في خلال هذه السلسلة والسلسلة السابقة السلاسل السابقة، وأيضا كتابي الحلقة 50 وأيضا 51 وأيضا 48 أظن في 48 الذي يتحدث على أنه النسبية الخاصة حسب معادلة الطاقة غير محفوظة عند وجود الجاذبية، فإن حتى نجعل النسبية الخاصة محفوظة في وجود الجاذبية فإن أو في وجود الكيرفتشر، فإن لا يجب أن نعدل في M small حتى تساوي المقام الموجود، يعني زيادة في M capital في المقام في معادلة الطاقة. بالتالي نجد أن في الكيرفتشرز الباورفول كيرفتشرز نجد أن الM small غير محفوظة، وهذا هو ما يحصل داخل الثقب الأسود. داخل الثقب الأسود كلما تقدمت الجسم الصاغر داخل الثقب الأسود كلما تقدم كلما محلت كتلته صغرت كتلته، وهذا يعني أن النسبية الخاصة غير محفوظة وأن السيمتريز غير محفوظة. الريجولاريزيشنز أو الفنايت إجبار الريجولاريزيشن طبعا يعني يتحدث بالضبط عن هذا الأمر. يعني الريجولاريزيشن تتحدث عن نظرية عليوسي بالضبط، وهذا أمر مهم جدا أننا نضع له اهتماما في المحاضرات القادمة. أما أن نجعل التيرمز كاونت التيرمز نجعلها فنايت هي محاربة الريجولاريزيشن، وهذا ما يفعله فضاء ثانوي الأبعاد. فضاء ثانوي الأبعاد يحارب الكتلة بهذه الأمور، يعني كأن الفضاء ثنائي الأبعاد يحارب الريجولاريزيشن. فضاء ثنائي الأبعاد لا يريد الكتلة تنقص، هو حافظ السيمتريز، وبالتالي قبل أن الكتل تنقص فهنا يطردها إلى الخارج بالنسبة في التفاعلات. بالنسبة لداخل الثقب الأسود بالمناسبة الفضاء ثنائي الأبعاد هو السبب في اضمحلال الكتل، لكن أتحدث عن الملاحظ الخارجي بالنسبة للتفاعلات دون المادية. فنجد أن الفضاء ثنائي الأبعاد يطرد الكتل، طبعا يطردها بماذا؟ داخل البروتون هي كتل صغيرة اللي هي كما ذكرنا الأب والداون كوارك، يطردها الفضاء ثنائي الأبعاد كتل ضخمة مثل الطوب كوارك. طبعا هذه الكتلة الضخمة لا تأتي فقط من داخل البروتون، إنما من داخل البروتون بالإضافة إلى طاقة التفاعل مثل الرسم البياني لماكس بلانك دياجرام. نجد أن تزيد الرسم البياني إذا عملنا الطاقة الدالة في أو الإشعاع الدالة في لامدا، نجد مع نقصان لامدا تزيد الطاقة طبعا، وبالتالي يزيد كمية الإشعاع الخارج من الثقب الأسود من الجسم الأسود، وهذا يعني أنه أغلب الإشعاع القادم من الجسم الأسود يكون ذات طاقة عالية، وهذا ما يحدث في التفاعلات الدون المادية، بحيث أنه كلما زادت الطاقة خرجت جسيمات ذات كتلة أكبر، لأنه طاقة التفاعل هي التي تعمل هذا، بالإضافة إلى أنه الطاقة العالية داخل البروتون هناك طاقة عالية كما رأينا، كما ذكرت أنه الكواركات لديها مومنتوم عالي ولديه كتل صغيرة أيضا، بالإضافة إلى طاقة التفاعل هنا تظهر جسيمات عالية الطاقة، وبالتالي كسر السيمتريز عن طريق الريجولاريزيشن أمر مهم جدا جدا يجب أن نضع له بالا. ربما أنا سأنساه في المستقبل، لكن أنا أريدكم أن تتابعوا هذه الفرضية التي شرحتها الآن عن الريجولاريزيشن، وأنها يمكن أن تؤدي إلى نظرية عليوسي مباشرة، لأنه تحارب الفضاء ثنائي الأبعاد وما يفعله الفضاء ثنائي الأبعاد. فبالتالي يمكنكم أن تصلوا لفيزياء جديدة أو تجارب جديدة في هذا الأمر. طيب تعال نواصل.
But the second part is to fulfill so-called renormalization conditions. Renormalization conditions are exactly the conditions which are, let's say, boundary conditions or requirements that the theory should fulfill after renormalization, which have the purpose of defining unambiguously the finite parts. And one definition would be simply to say the finite parts are zero in dimensional regularization. In other words, the counter term Lagrangian contains purely 1 over epsilon poles. But this is a choice which is difficult to make if you do not use dimensional regularization. So some other person who uses some other regularization method, for example, lattice discretization of space-time, they would not know what it means to use only 1 over epsilon poles. So it's a choice which is possible but specific to dimensional regularization. Another choice which you might have learned about in your past quantum field theory lecture are so-called on-shell renormalization conditions, which have, for example, the requirement that you say, after adding the counter terms, my green function is 0 at a particular momentum choice. So for example, you might say at p square equal m square, the green function vanishes. Or at p square equals 0, the green function vanishes. You can always achieve this by adding a finite counter term. And so such a thing would be an on-shell renormalization condition. And these are possible ways to fix the finite parts. Okay, anyway, so that must...
طبعا الرينورماليزيشن يعمل عكس ريجلايزيشن، يعملان عكس بعض. فالرينورماليزيشن يعمل على استعادة التناظر، والريجلايزيشن يعمل على كسر التناظر.
be done. After you've done these steps, the theory is renormalized at the n+1 loop level, and you can go on with the iteration. So let's just write down the resulting outcome. So A, you have now a bare Lagrangian at the n+1 loop level, which is given by the classical Lagrangian L0 plus all the counter term Lagrangians up to the n+1 loop level counter term is defined such that the theory is finite at the n+1 loop level. Question? And this is basically saying that the iteration from n to n+1 is complete. So at this point we can go on and do the next loop level, and we know that we will succeed in renormalizing our theory at all loop orders. And then we have at all loop orders a finite theory, and the second outcome is what can we do with the finite theory. This is now a consistent quantum field theory, finite and consistent with the basic postulates, namely locality, relativity, and unitarity and causality of the S matrix. These are the most important quantum field theory postulates. They are all fulfilled in the limit epsilon going to 0, and therefore we can now compute physics. So physical results at the any order, let's say n+1 loop order, are obtained how? They are obtained from these renormalized green functions. Green functions derived from Feynman rules given by the Lagrangian L bare up to this order. In other words, taking into account all the counter terms up to the loop order we are working at. And then the green functions are finite, and the physical result is of course obtained in the limit epsilon going to 0. So by taking the limit epsilon going to 0, which exists. But there is another detail, and by neglecting d-4 dimensional parts of objects such as gamma mu, a mu of x, etc. Okay, so in, for example, gamma matrices, the index mu would in dimensional regularization run from 0 to d-1, and so you have a superfluous set of gamma matrices, and you simply ignore all these additional gamma matrices which are not existing in 4 dimensions. You set them to 0. So this is not mathematically contained in the limit epsilon going to 0. So if you have a function which depends on the variable epsilon, there you set epsilon to 0, but here epsilon doesn't appear. There is just a set of additional gamma matrices, and you set them to 0 by hand on top of taking the limit. So this is what you do. These quantities are called evanescent. So the statement would be that in the finite theory, you set all the evanescent quantities to 0. And then you have constructed a complete four-dimensional relativistic quantum field theory, which is in line with all basic postulates, and in this way, you've renormalized the theory. Okay, any questions? Yep.
Say, for example, one would try to guess this counter term for n plus 1 loop level. Is there an easy way to check whether that is a correct counter term?
Correct in what sense? Whether it makes it finite or something else? Yeah. So only by calculating the whole set of diagrams. That is the only way. Yeah.
In the beginning, you said that the renormalization scheme is necessary because of the ill-defined operator products, and it kind of feels like we're setting up a wrong theory and correcting it iteratively. Why can't we just set up a correct theory?
The correct theory would be the regularized theory. So, but okay, in dimensional regularization, you kind of circumvent the operators, but there would be also ways to regularize directly the operators. For example, if you set up a space-time lattice, this is lattice field theory, then you replace space-time by a finite lattice where you have a finite lattice spacing and also a finite number of lattice points. So you have both an ultraviolet regularization because you have a minimum distance and also an infrared regularization because you have also a maximum distance. And then on these finite number of lattice points, you define the field operators. This basically becomes then an ordinary quantum theory, not a quantum field theory with a finite set of degrees of freedom. And then the distribution product become ordinary operator products and everything is defined. And then you would set up your theory in this way. You can compute everything, but you go through the same procedure. And at the end of the day, you take the limit where the number of lattice points goes to infinity and the lattice spacing goes to 0. Then you encounter the same divergences and you renormalize the theory by adding some counter terms to your definition in the Lagrangian. And then again, you encounter a finite continuum quantum field theory as a limiting theory. But it never happens that, I mean, okay, this would be kind of maybe also a dream of a mathematical physicist to set up a mathematical structure where the operator products are directly defined. And there are also approaches in these directions, but they are calculationally not so well developed. And therefore, in perturbation theory, we rely basically on Feynman diagrams and not on the operators. Yeah.
So, if I understood correctly, we have certain ambiguity in the counter definition of the real part. So,
yep.
So I define that, and so depending on how I define these counter terms, I will have different expressions for Green's function, for normalized Green's function.
Yes.
How at the end I get agreement with the physics, because the physics is
very good. So we should discuss this also in the next lesson. But indeed, in the beginning, I had a condition. We have correctly renormalized up to n-loop level, and here you now see there is not one way which is correct, but there is an infinite number of ways to make it correct. Namely, the divergences are unique, but the finite parts of the counter terms are basically your choice. And so this is this is what you have to achieve. Cancel the divergences, and then you get an infinite family of correct renormalizations by shifting around finite parts. And the theories arising in this way, they simply differ by the parametrization. The parameters appearing in the Lagrangian have different meanings. And person A calculates with one set of finite parts, and the electric charge means one thing. Person B calculates with different finite parts, and their electric charge means something else. But they would be able to relate electric charge A is equal to electric charge B plus higher order corrections. And if they use this relationship, then all observables become equal. So the physical content of the theory is actually unambiguous and it is uniquely fixed, but the parametrization is up to you.
ربما سمعتم هذا أمر واضح جدا جدا. الإلكتريك تشارج تختلف في الأبعاد، وهذا ما أو في اللبس، وهذا ما يعني ذكرته أنا سابقا وما زلت أذكره مرارا، أنه الكميات تعتمد على الملاحظ، تعتمد على الأبعاد بسبب ما يسمى بالسبيس تايم كونتراكشن والسبيس تايم دايليشن. فالسبيس تايم كونتراكشن تؤثر دائما في الكميات، حتى الكتلة تتأثر بالسبيس تايم كونتراكشن، الشحنة تتأثر بالسبيس تايم كونتراكشن، المومنتوم يتأثر بالسبيس تايم كونتراكشن، فكل هذه الأشياء تتأثر بالسبيس تايم كونتراكشن. وإذا أصبح الملاحظ الذي هو في وضعنا الطبيعي إذا صغرت أبعاده حتى وصل إلى تلك الأبعاد الصغيرة، فإنه يرى الأمور طبيعية، لكن هو أيضا يكون متأثر بالسبيس تايم كونتراكشن، لكنه يراها طبيعية. أما الملاحظ الموجود في وضعنا نحن حاليا، يعني الملاحظ الخارجي، لا يشعر بالسبيس كونتراكشن، لكن يشعر بأن هذه الكميات اختلفت. هذه الكميات اختلفت، سيشعر بذلك أنها اختلفت، وسيشعر بها في أشياء أخرى. يعني نحن نرى أن الكتل تأتينا من المفاعل الهيدرونات الكبير مختلف أنواع الكتل، هذا ما نشعر به. لكن هل هناك مختلف أنواع الكتل الشحنات؟ نحن نعلم أن الشحنة تنكسر، السيمتري الخاص بالشحنة تنكسر، فالكواركات تأخذ تلت من شحنة الإلكترون و2/3 من شحنة الإلكترون. إذا الشحنة أيضا انكسرت، السيمتري الخاص بالشحنة أيضا انكسرت، وهذا ما نراه نحن. لكن لا نعرف أن هذا بسبب الأبعاد، أو ربما يكون هناك تطور في علم الفيزياء. أنا لا علم لي، لكن ربما يكون هناك تطور في علم الفيزياء وأوجد أن هذا بسبب الأبعاد. لكن الآن نظريتي تخبرنا بغاية الوضوح أن الأبعاد هي السبب في هذا النوع من الكسر في التناظرات.
And basically it is as simple as this. If you have some physical result, let's say you predict some observable as a function of one parameter. Of course, this is your parameter, person A. Nobody can stop a person B to define a parameter of person B equal to any function f of CA. Or maybe let's do it the other way around. So you simply like this parametrization better, you put it in, and then you get this. You have reparameterized your theory. The theory is of course the same. All relationships between observables cannot change in this way, but the formulas expressed in terms of CA or CB look different, of course. But this is exactly what happens, nothing more than this. Not necessarily constants, but relationships between observables. The physical content of the theory lies in the relationship between observables. So if you measure one observable, you can predict the second one as a function of the first. But typically predictions work by using some parameters like charges, masses, and so on. And the parameters might not be directly observables themselves. So you predict many observables as a function of many unphysical input parameters. You could in principle completely eliminate these unphysical input parameters and directly express all observables in terms of some other set of basic observables. And then you completely eliminate this freedom of parametrization. And that might be the choice of person B, that they say, okay, I do not like these unphysical parameters, I replace them by basic observables. Yes.
Can we say something like that the theory is uniquely determined just by the divergencies of this L0 Lagrangian?
The theory is, in that sense, you see it, it is basically uniquely determined by L0. Once you specify L0 as the start of the iteration, everything else follows automatically up to those ambiguities in the parametrization.
I mean, if it's uniquely defined just by looking at the divergences of the zero, not even looking at the zero.
It's not uniquely defined by the divergences. Yeah, no. And they drop out at the end anyway, so they are unphysical. Okay. Then let us continue on Wednesday. On Wednesday, I might do a little bit of lecture, but for sure we will also continue with the exercise sheet. Depending on how far we get, I might do a little bit of lecture too. Okay, so welcome back to the EFT lecture. Today we will finish our